Now, I put a large emphasis on using models in chemistry. Here's some models that you're going to get familiar with this semester. Anyone know what this molecule is? It's not H2O, although it could be. What do you think it is? And it could be carbon dioxide. It could be H2O because you've got two colors of one type and one color of another. That's like H2O. Okay. But as you'll learn later in the semester, if I build a model of H2O, it's not going to be in a straight line like this. H2O is going to be bent like this. This one's carbon dioxide. It's in a linear form. It's got these springs. You're going to learn what these springs are. See, a model is only so good as it is if you understand what the model is interpreting. Models are used for us to understand what we can't explain easily, what we can't see. I have no idea what CO2, carbon dioxide, actually looks like. We don't have microscopes that are that powerful, okay? But we have other ways of measuring the molecules, and using science, we can then infer from that data what the overall shape would look like. And this model does a really good job of showing us what the bonds look like, the chemical bonds. These are double bonds between what's red is oxygen and what's black is carbon. But you needed to know that, all right? So a model is only as good as your understanding of what it's showing. So when you see a ball and stick model like this, all right, the red is oxygen, the black is carbon. You don't really need to write this down. Blue is usually used for nitrogen. So this is a model of how nitrogen exists in nature. Nitrogen in nature is actually a diatomic molecule. It's together two atoms of nitrogen are bonded together. That's its most stable configuration. That's how you find it in nature. You'll be using other models to describe what nitrogen looks like. You might have a model that looks like this with 3 lines and 2 dots on either side. I'm not going to explain what that model is now, okay? These are all models. Figuratively speaking, half of this class, half of your learning in this class is learning how to interpret models, all right? And in interpreting the model, you'll be able to then understand better the underlying chemistry that is being modeled. Here's some more, all right? In this case, the balls are atoms and the sticks are bonds. And we've got a single bond here. We have one stick, so that's a single bond. Here's another double bond, all right? We'll be learning about all this stuff this semester. These are covalent bonds. You have to know, right? Like I said, the black is for carbon, so I'll put a C here for carbon. Now, why is it a ball, right? We'll be talking about models of atomic structure. In this ball, this is a space-filling model. At the center of this ball is the nucleus, and then the rest of the volume is taken up by the electrons. We'll be learning about that. The red is for oxygen, so you're also going to be learning about the symbols for the elements. Here's a periodic table hanging for you in the lecture hall, although probably most of you can't read what's on there because even though they're big, it's still really small to read. It will also be in the slides that you print out. Here, I'll just show it to you. It's a nice standardized periodic table. It's nice and big. You can read everything on it. But what's not on this periodic table is the spelling out the names of the elements. That's something that I'm going to expect you to learn on your own. Now, many of them are used commonly enough that you're going to know what they are, right? We've been using C for carbon, O for oxygen. Most of you know those, right? You probably know what P is. What's P? It's not potassium. It's phosphorus. Potassium is K, all right? Yeah, some of them aren't so straightforward, all right? You have to know them. I try to use some common ones over and over and over again to help emphasize. But at some point, not today, not yet, at some point, I'm going to be having you learn the names to match the names with these elements, at least for some of them, for the first couple of rows of the periodic table. That's coming up later, okay? We're going to be learning about other ways to represent what these molecules are. This is a ball and stick model. If I were to write the structural formula for this, I might draw it out like this. Again, it's using another model. This is very similar. I might draw it this way. You're going to need to know how to interpret that. Or we might write it as a molecular formula. In this case, the molecular formula, I might write that as C2H4O2. Or some of you who go on to organic chemistry might write it as CH3COOH. Right? Different ways to describe the same thing. Anyone know what this molecule is? Go for it. Ethanoic acid. That is the IUPAC correct name in organic chemistry for this molecule. It goes by another more common name. All right, ethanoic acid is correct, but anyone know what the more common name for this molecule is? This is acetic acid, which is a common component in vinegar, which I like using a lot for in examples. Vinegar, which I'm sure everyone is familiar with, vinegar is not an element. You don't have vinegar on the periodic table. Vinegar is a solution. It's a 5% solution of acetic acid in water, in H2O. All right. I also gave you a challenge to watch the videos online for some of this easy to get content, simple definitions and explanations. And your notes should look like this now for these next couple of slides, all right? And I took a look about 10 minutes ago, and about a third of you also failed to meet that challenge, all right? We're only in the second lecture now, folks. So remember that this video content is important and it's part of the class. Now, not every chapter is going to have this many videos to watch, as I mentioned the last time. There's a few more this time just because this is the introductory chapter and there's just so much in definitions in that we don't need to spend time in lecture for me to explain to you the difference between a solid, a liquid, and a gas, all right? But there's some essential definitions in there that I want you to all to be familiar with and to know. Every science class, the textbook has a little section about the scientific method. And I'm sure you've all heard it before. You make observations, you make a hypothesis. From that, you make a prediction, you test that prediction, you analyze the results, you come up with theories and laws, blah, 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 blah. And then that's it. And then they move on to the science. But I want to spend a significant amount of time with you this morning actually talking about the scientific method to really understand what it involves and then what we get from it. Because science and following the scientific method actually gives you a truth. And it's not a truth in the sense that, oh, I believe this. It's what we call a scientific truth. It's what comes from the practice of the scientific method. It gives you a result that you don't have a choice whether to believe it or not. It's not how you feel about it. This is what the scientific method has shown you about the truth of the system that you are studying. And I make a big deal about that because especially in these political times, you hear lots of stuff about truths and not truths, and science and non-science, and what's believable and what's not believable, and what's denied and what's accepted. And that's really not the right way to think about it, because that's not what the scientific method is. So if I teach you anything in this class, I want you to at least leave this class at the end of the semester understanding what science actually is and how we use the scientific method. Now, this also isn't the history class, all right? But we're going to be looking at a lot of historical experiments to help you understand how the scientific method was used to help us sort of evolve our understanding of how chemistry works. What's the structure of an atom, right? We can't see an atom. We don't really know what it looks like, but we're going to go and look at some of the experiments over the centuries that that took place to help us understand better how things are actually operating at a level where we really can't see it. So it's already up here for you on the slide. You make observations. Let's say I want to do a study. Because I'm sure there are many of you out there who aren't wearing the blue today. The point is that I make these observations, and from them, I make a hypothesis. And this hypothesis, at the very beginning, this is a limited complexity hypothesis. Starting out, I don't really have a lot of data to work with. I'm interested in studying this subject, but I really don't know, right? So I make a limited complexity hypothesis, and then I make a prediction, and I'll go ahead and I'll test that hypothesis with some scientifically designed experiment, and I'll analyze the results. And from those results, I'm going to see whether or not they support or not support my hypothesis. All right, so we go through the process, we test, we analyze, and I find that, well, okay, my original hypothesis really wasn't that good, was it? Because I'm sure there are many of you out there who aren't wearing blue today, okay? So we'll go back, and I'm gonna go ahead and I might repeat the experiment. When I repeat it, I might refine it. I might need to go back and refine my predictions as well. I may even have to go back and refine my hypothesis. I might even have to go back and make some more observations. The point being is that we need to repeat the experiments. Even if you don't make modifications, you never measure anything one time. Now that's kind of, that's not kind of a fallacy, it's true. You can't learn anything by just measuring it once. However, when you do your laboratory experiments all semester long, you're probably going to only be measuring things one time. So that's not really showing you the reality of science, unfortunately. So I will keep reminding you from time to time that you have to repeat your experiments. It's called research for a reason, because you're repeating what you're doing. And sometimes you're just repeating it just to get an idea of what the error of your measurement is. And in this case, when we repeat it, we're going to make some refinements. We might need to make some modifications as well. That's not modification, let's just modify. And we keep repeating this as long as necessary. Sometimes we might have to go all the way back and change the overall setup. Just change the idea. And ultimately, we keep doing this. Thank you. We keep doing this until we either support or we reject the hypothesis. So obviously, if we reject it, we're going to go back and do this. But we keep doing this until it's supported. And then when it's supported, we know that we have something substantial. Right? We have good tests, we've repeated them, we've refined them, we have supported our hypothesis. All right, so now what are you going to do? What do you think the next step would be? Share it. Share it with who? With other scientists. All right. How do you do that? How do you share your information with other scientists? Anyone know? Go ahead. Say what? Create a theory. All right. Now, creating a theory is going to come soon enough. All right. But how can you, if you create a theory, you're creating it yourself. How do you share that with the other scientists? Go ahead. Submitting it for peer review. Okay. You could also go to a scientific conference and present it there, but it's really not your own until you have it published somewhere. And you do that by submitting it for peer review. So let's put this, we're going to publish our results. Publish, and this is done through something that's called peer review. Now, what does peer review mean? What's a peer? Anyone know? Someone else, like you probably know what a peer is because you said it. Yeah, so you said a scientist in another field, well, probably in the same field because they have to know something about what you're doing. But a peer is a friend. I think if you look up the word peer in the dictionary, it will say friend. But in science, a peer isn't necessarily going to be your friend, right? It could be your enemy. It could be your scientific rival who you went to graduate school with and doesn't believe anything that you say. But hopefully they're impartial enough to review, critically review your paper, okay? And it's not just one. When you submit a publication for review, or when you submit a paper for publication, it's reviewed by 2 or 3 or more scientific peers. These are people that are in your field, okay? But these could be friends, they could be colleagues, or they could be rivals. Okay? And they all look at your publication, they look at the data, they look at the experiment, they see if it was set up correctly, if it was interpreted properly, they give comments back and whatnot. They go to the editor, and through that process, it then, if it passes, then it gets published. And when it gets published, now it is accepted into the scientific community. That is the fundamental way that we communicate our results to the rest of the scientific community. And it's been that way, maybe not through peer review in this current process, but it's been that way throughout the history of the scientific method. It's part of the process, but it doesn't stop there, all right? Because if it's something that's worthwhile, if it's going to end up being a theory, if it's going to end up being a scientific law, that means it's more substantial than just what you thought, or maybe it is as substantial as you thought, but other people need to verify that themselves. So it doesn't stop at the peer review stage. Once it gets published, now it needs to get validated. And the validation is also done by your peers. It's done by other scientific laboratories because your work is so interesting that they're going to try to repeat it. So these are also by your friends and by your rivals. Oh, I saw that paper. That guy's an idiot. He doesn't know what he's talking about. I'm going to go ahead and do his experiment again. I'm going to prove that guy wrong. And it turns out, hey, he was right after all. Or maybe they'll make it their own improvement on it. Say, he didn't think about this. Or what if we now try something else? Hey, if I'm not interested in it, I'm going to make my own extensions. All right. This is happening now, and it magnifies. So now you don't just have one lab, but you've got 10, maybe 100 labs or more around the world, right? Doing this validation. And every time something gets validated, now, if they find the same result, there's nothing new to publish. If you're going to publish again, it's got to be something new. So they might refute what I say and come up with a better test or a better explanation. They might publish that, or they make their own extension. The point is that through this validation process, it then goes back into peer review. Okay? And we start that process all over again. Now it gets reviewed by other people. Sometimes it's the same reviewer, sometimes it's different. And this goes round and round and round and round. Now that's if it's validated. If it's refuted, then we go back to the drawing board, so to speak. Okay, but if it's validated, then it goes back into peer review, and around and around and around we go. So it really is a complicated process. And as it gets more and more validation, it gets improved. So validation and improvement. And this cycle keeps on going, it keeps on going. And as the body of evidence builds and continues to build, we end up getting this scientific truth emerging from the process. So let's call this an emergent scientific truth. And again, this isn't a truth like I choose to believe it, right? It's a scientific truth. This is the result of the scientific method. You don't have a choice whether to believe it or not. It's not, it doesn't work that way. This is what the science has shown you. Whether or not you choose to believe that, you know, oh no, this goes against everything that I've ever thought for my entire life. It doesn't matter. If you do the scientific process the right way, that's what the science is telling you. It's probably the best invention that human beings have ever come up with as a way to really discover how the natural world works, right? But it needs to be understood and it needs to be practiced in the right and honest way. It's from these scientific truths that then we get things like scientific laws, and scientific theories. Now you might be wondering, well, what's the difference between a law and a theory? And, you know, it's subtle. We can think of laws and theories of being the same thing. If you really want to know, I wouldn't test you on this, but a scientific law is more describing a phenomenon, whereas a scientific theory is explaining the how and why that this works. But for our purposes, we're just going to consider these to be one and the same. If you're talking about a scientific law or a scientific theory, it is something that has gone through this process, right? So it's not something that you can just conveniently deny because you choose to, right? So that's my little speech to you about the scientific method. And you're going to see this in play as we go through this sort of history lesson as to what happened in chemistry to bring us to the information that you're going to be studying in this class today. Now, as I mentioned, it's not a history class. I do put dates on here and I do give you names, but I don't test you on what date was this experiment done and who did this experiment. If I were to give you a test question about an experiment that we talk about, I'll tell you who did it. And I'll tell you about the experiment. And that kind of question would then be about, well, what did they do in the experiment? How did they interpret the data? Did they make the conclusion based on this information or that information, right? It's not just a recall, who did it and when was it done and what was that experiment about? All right. So we're going to talk about Joseph Proust and John Dalton. And this work was done, Joseph Proust, this was in the late 1700s. And again, this is just to put it into context for you. And what Proust was doing was working with metals and working with oxygen. By the way, I should mention our periodic table here with over 100 elements on it. They didn't know all of these elements in the 1700s. They only had a handful of elements that they were working with, okay? Metals, they knew about oxygen gas, and Proust was doing lots of experiments mixing metals and oxygen. And analyzing the results and learning some pretty interesting things about the results. And mostly is that they were always in the same proportions. For example, H2O. Doesn't matter how much H2O gets analyzed. When you mix hydrogen and oxygen, you make H2O, and it's always going to be 11.2% hydrogen and 88.8% oxygen if you were to measure it by mass. And that's going to be true whether you measure a little tiny bit of it or whether you measure a whole large amount of it. The proportions of hydrogen and oxygen were always the same. All right, so they always mixed
with the same elemental composition. And in fact, his scientific law was called the law of constant composition, which is just written right there for you on the slide. So we'll actually be doing percent mass composition later on in chapter 7, and you'll be doing a lab experiment on percent composition. So this is percent composition by mass. And it was pretty powerful at the time. I mean, to you all, it seems like it's no big deal because we all know what H2O is. And you can see from the way it's written on here, there's 2 hydrogens for every oxygen. So that's some kind of a ratio, and we'll be studying those ratios in class. So it's not too surprising that it should always be the same. But back in the 1700s, when they're just trying to figure this stuff out for the first time, this was pretty revolutionary, okay? But through the scientific method, there are sometimes rivals as in your peer group, and there's also skeptics. So there were some people that were skeptical about this. Now, why would they be skeptical? Because they probably did some experiments that didn't seem to follow this law of constant composition. So the skeptics, they would mix tin with oxygen. Let's spell oxygen the right way. And they found different things coming out of it, not just one thing with the same constant composition. They found 2 types of compounds. One had 78.8% tin and 21.2% oxygen. And another one had 88.1% tin and 11.9% oxygen. So they said, well, Krauss, you don't know what you're talking about. Here, we just did your experiment, your big famous experiment. We just did it with tin, and we got a whole big mess out of there that we don't understand, okay? Now, that doesn't mean that Proust was wrong, okay? If we go back to, maybe he was wrong to call it a law just yet, okay? But if you go back to the scientific method, you don't necessarily refute the whole thing, but you might have found evidence for something that doesn't get explained perfectly by the existing theory. Now, that brings up another comment that I mentioned to you at the last lecture about using models. Right? We use models a lot in chemistry, in all science, and the models are designed to explain something that's much more complicated than we can really see or understand with a simple ball and stick model, but it works pretty well, and it explains lots of things. And when the model stops to explain everything, then we need to come up with a new model that does explain the new evidence. Well, the skeptics came up with new evidence, and we need to modify this model through the scientific method to explain these results with Proust's model, or if we can't, then yeah, we might need to throw Proust's model completely out and start all over again. Or I guess the third option is we don't understand anything about what's going on, so we're just going to wash our hands and move on and do agriculture. Fortunately, that's not what happened. So the next big improvement on this came from John Dalton. And this wasn't too far down the road. This was in around 1803, when Dalton took a look at all of this data and he recognized something new in the existing data. And that new recognition was that, look, let's take a look at these things that came out from, say, for example, when you mix things with tin and oxygen. If you take this ratio here, this ratio, if you did it by math, this would be 0.269 as a ratio. And you take a look at this ratio of tin to oxygen in the other compound that was made, and that has a ratio mathematically of 0.135. Now that alone doesn't seem too surprising until you realize that this is a simple twofold increase. There's a twofold difference between one ratio and another ratio. Nice small whole number ratio. Now, it wasn't just with tin and oxygen that Dalton recognizes for. There are lots of other examples of this, okay? And what this led to was a modification of Proust's original model to, we still have constant ratios, right? But now these ratios could be between multiple compounds that are made with the same elements, but those ratios will always produce things in small whole numbers, like twofold and threefold and fourfold, never 2.345 or 6.243. You know, it's always just a nice small round whole number, and it's usually pretty small, like 2, 3, or 4. Not usually much more than that. For example, H2O, right? There's a small whole number ratio there. Now, they didn't know this at the time. I'm going to fast forward now to our modern understanding. We know what's going on here, okay? We know what these two materials are. It turns out that tin, by the way, who knows what the chemical symbol for tin is? Anyone know? What is it? It is SN. Very good. What does SN stand for? Anyone know? Stannous. Stanic, Stannis, Stanin, whatever. It's not always English, folks, right? There's a lot of Latin in here. Sometimes there's other German, French, all sorts of languages go into these. Yes, question. How did I get the 0.269 ratio? If you take 21.2 and divide it by 78.8, you should get 0.269. I think. I brought my calculator. That's what my notes say. 21.2 divided by 78.8. Yep, 0.269. So that's a great example. If I show you something and it doesn't make sense to you, raise your hand, say, you know what, can you explain, where did that number come from? All right. And hey, sometimes I make a mistake too. Okay, I'm not perfect. I'm a human being just like all of you. Okay, so there are, you know, sometimes I get really hyper excited and I go off and I try to do things in my head when I shouldn't, and I'll write something down that's not right. Go ahead and stop me. I think you made a little boo-boo over here, and either you're right or I'm right. Either way, you bring it up and the whole class gets to see it in action. All right, so SN, that's for tin. And as we'll be learning later on in this class, tin can form ions. We'll be learning about ions and what they mean and how they form and why they form. And tin can actually exist in two different kinds of positively charged ions. We have tin that has 4 charges, 4 positive charges, and we have tin that has an ion with 2 positive charges. And when those different ions combine with oxygen, they combine in 2 different ways. If it's tin 4 plus, the compound that's made, we call that tin 4, Roman numeral 4, oxide. And when the tin and oxygen combine, when tin is in the 2 plus state, we call that tin Roman numeral 2, oxide. And again, we'll be learning all about those details later on. And the chemical formulas for these, right? Tin 4 oxide, we would write that as SnO2. And for tin 2 oxide, we would write that as SnO. And you're going to learn how to understand that as well. But in doing this, notice that we not only have a ratio of oxygen and tin in each compound, but we also now see the twofold difference. The twofold, this 2 here, comes from one of them having 2 oxygens and one of them having only 1 oxygen. Okay? So what Dalton basically did was merged his law of what he called multiple proportions, right? It's just an extension of the law of constant composition, right? He merged both of these laws to really give us the first theory of how these elements interact. So the first theory of atomic structure. In fact, it was from that work that we have the word atom, right? Dalton, part of his theory was that these elements interact in ways that give us these small whole number integers, or small whole numbers, I should say, right? And his theory basically says that these elements, like tin and oxygen, these are composed of atoms. Oh, let's give us some more room to write atoms here. And that these atoms for the elements, these are discrete things that can't be cut in half, that can't be reduced any further and still be atoms of the element that they are. And what I'm talking about there is things that behave like that element. Tin behaves a certain way. It has what we call physical properties and chemical properties. Now, those you learned about in the video content, okay? So atoms, these can't be reduced any further and still retain their physical and chemical properties. Here, I'm writing all over the next slide here. Please don't write onto your next slide. You have margins to write in. I have other stuff that I want to put on the slide, but I don't have margins to write in like you do. Properties. Now you have to know what those are, what we mean, the difference, right? There's video content for that. I'm not going to lecture on the difference and the definitions of physical and chemical properties, but they are specific to the element that you're studying. And this idea of the atom is that that's the smallest fundamental unit, okay? The atom, the smallest fundamental unit of the element. By fundamental unit, because if you reduce it any more than that, then it's no longer a fundamental unit. It's lost those physical and chemical properties. It actually comes from the Greek word atomos, which is Greek for not cutting. Not that I would put that as an exam question, but it's a little bit of trivia. You can impress your friends. That's where atom comes from. Do you know why you can never believe what an atom tells you? Because it's making everything up. There you go. Thank you. All right, so we're going to depart now from models of atomic structure. We're going to revisit the scientific method and building from Dalton's theory. All right, I'll tell you more about Dalton's theory later when we get back to this in chapter 2. All right, we're going to pick up the history lesson there. But we're going to now turn our attention back to more of the fundamental introductory stuff of chapter 1. Now, I've written all over this slide, so I'm going to just go ahead and make a copy of this one, so I have more space to write here. All right, so this is a bit of an extension. We talked about mixtures, things in proportions in mixtures, and now we're going to talk about more of how we work with mixtures in science and in chemistry, and getting to know some of the names of these things. And again, it's a way to help us organize our natural world. Okay, so mixture. So we just made a joke, right? You can't believe what an atom tells you because they make everything up, right? So atoms, elements, right? Matter, right? Matter is something that has some mass and it occupies some space, right? And we can classify all matter in a couple of simple ways. We have things that are pure and we have things that are mixtures, right? So it's either one or the other. You're either pure or you're a mixture. But we have different kinds of pure matter and different kinds of mixtures. So let's talk about them a little bit separately. That's all laid out for you here on this slide. So if you're pure, we can classify that in two different ways. We have elements and we have compounds. Now, elements we've already talked about. Things like hydrogen. What's the chemical symbol for hydrogen? Everyone should know this one, right? So elements, hydrogen. What's the chemical symbol for oxygen? O. And you mix them together and what do you get? H2O. You get a compound, H2O. But it's still pure H2O. There's nothing else there. Okay, you get what I mean? So you can have a pure element or you can have a pure compound. And here, this is gold, a nice bar of gold. Who knows the chemical symbol for gold? Someone said AG. AU, it's AU. Yeah, that's AG is what? No, it's not aluminum. Aluminum is AL. It's all right, it's silver. AG is silver, AU is gold. And you'll be learning soon enough where to find all of these on the periodic table as well. Okay, so this is H2O, but it's still pure. There's nothing else there. Now, mixtures, we have two different kinds of mixtures, but first, let me just say that a mixture is, as it sounds, right? You have two things that separately they would be pure, but now you've mixed them together. And you can tell the difference between something that's pure and something that's a mixture by being able to separate it by some physical process. So let's highlight that. If you can't mix it by a physical, if you can't separate it by a physical process, then it was pure. And what do I mean by separating from a physical process? This could be something like, whoops. This could be something like filtration. It could be distillation. And don't worry if you don't know what some of these words mean. It could be, you can separate things by magnetism. It doesn't matter what the technique is. What matters is that they retain their same physical and chemical properties. Once again, I refer you to the video content to understand what we mean by physical and chemical properties and what the difference is. Yes, question. What about fire? What do you think? That's a great question. Is fire a physical separation process? What do you think? Show of hands. Who thinks fire is a physical separation process? Who doesn't? All right, well, the hands are against you. Why would you think fire might be? Okay, it's all right. For those of you who don't think that it's a good process, why? I don't want to call them the same people all the time, but they're the only ones raising your hands. Go ahead. So this student was talking about combustion and oxygen chemical change. That's exactly right. The reason you can't use fire is because combustion, right, what fire is, that's an actual chemical reaction. And when you do a chemical reaction, you actually are making new products, all right? You're doing a chemical change. So you're not retaining the same physical and chemical properties because you're making new products and they will have their own physical and chemical properties. All right, so the litmus test here, I shouldn't use that term. The way you know whether or not you can make the separation or not is by seeing if it retains the same physical and chemical properties. If it does, if you can separate two things out and they've retained the same chemical and physical properties, then they were in a mixture. If you have a new chemical and physical property in that mixture, if you took hydrogen and you took oxygen and you mix them together, you've now made something new. You've made H2O. H2O has different chemical and physical properties than either hydrogen or oxygen alone. Now we can separate them. There is a way to do it. It's called electrolysis, but that's adding more energy, and we're actually breaking bonds. We're breaking covalent bonds, and you'll learn about those soon enough. We're breaking covalent bonds in the molecule to separate the H2O into H and O, okay? So it's gotta be a physical process that doesn't add extra energy to break bonds. It's just, can you separate them somehow? And that separation is based on the chemical and physical properties. Now, if you find that you do have a mixture, there's two kinds. There's homogeneous and there's heterogeneous mixtures. Homo is the same, and hetero is different. And in this case, by same, what we mean is that you can't see any difference. You cannot see the individual components. Whereas if it's different, you can see the individual components. Now, the example here is Italian salad dressing. Who likes Italian salad dressing? Right? You don't like Italian salad dressing? Wow. But you've all seen it, I assume, right? It's got herbs and stuff in there. It's got oil, and it's got what else in there? Is it water? It's vinegar, oil and vinegar. Most of you probably already know that oil and vinegar don't mix. One of them is very hydrophobic. One of them is very hydrophilic. Those are terms that you will learn much later, okay? And if you just put it, and there's lots of little herb chunks in there, okay? So there's all sorts of different things in this mixture, but you can see the individual components. Even if you took it and shook it up a lot, you can still see that there's individual chunks of herbs floating around in there, but you put it down on the table for a while and they will naturally separate, okay? Whereas if you just take a look at vinegar, I already told you what vinegar was last lecture. Who remembers? It's acetic acid. You remember the percentage? It's a 5% solution, which is a mixture of acetic acid in water. But you can't see the acetic acid. It just looks like a glass of water to you until you drink it. Surprise. All right. Now, I can clearly see that there are individual components in Italian salad dressing. If I gave you a glass of chocolate milk, all right, and I put it on the table, I would say, do you think chocolate milk is a homogeneous or a heterogeneous mixture? Who thinks it's homogeneous? All right. Who thinks it's heterogeneous? All right. For someone who said homogeneous, why? Say that? So he said you can't see the individual components, so it all looks the same. All right, that's great. Right? But you raised your hand thinking that it was heterogeneous. Why?
Because if you let it sit for a minute, it separates. You know, it has like
Oh, does it? You put
syrup.
too much syrup in your chocolate milk.
I mean, you know.
So okay, so she said if you let it sit, kind of like the Italian salad dressing, it will settle. I didn't expect that. So let's pretend that you put them, you know, in the right proportions that wouldn't happen. Okay. All right. So the point I'm trying to make here is that it really is relative to how you're looking at the material. All right. So the first suggestion that it all looks the same. Yeah, that's true. If you just look at a glass of chocolate milk, it should look the same, assuming you have the right proportions. Okay. Now, if you zoomed in on a microscope, you might be able to see individual molecules of proteins
that come from the milk and other proteins that come from the chocolate syrup, okay? So you could always make an argument that, well, it's heterogeneous because if you look carefully enough, you can see the mixtures. Here's another example. One of the buildings across the lawn from our building, all right? Anyone know what color it is? It's red, isn't it? I think it's red, okay? Can you tell, is it just painted red or are they bricks of red? Bricks. Are you sure? From here, can you see that they're bricks?
Yeah.
Are they all the same color or are they different colors? Right. The point I'm trying to make is that the farther away you get from that building, you can still see that it's red, but you might not see that it's made of bricks, or you might not see that the bricks are actually of different color. If you're standing right in front of that building, you'd say, yes, this wall is a heterogeneous mixture because I can clearly see the different components. But if you get far enough away, just like far enough away from the glass of milk, chocolate milk, it might look homogeneous. So it really is relative how we classify these things. And the general rule we follow is that you can see different individual components with the naked eye, not microscopically. Okay, so it's just a general way for us to classify certain materials, and we're going to be talking about things that are pure, and later on in class we'll be talking about things that are in mixture, especially homogeneous mixtures, because this is going to be the stuff of solution chemistry that we're going to do later on in chapter 8.